Exam Wrapper 2, Morgan Jackson, Section MO2, Dr. Greco. Let's begin looking at the question. This problem says, consider 4 stars, each of mass m, which interact via the gravitational force. The net force of the masses on one another results in a uniform circular motion of all 4 masses at a constant speed. Calculate how long it takes for one of the masses to make a complete revolution. You can assume that the velocity is much less than the speed of light. Hint, consider the parallel and perpendicular components of all the forces. To begin this problem, let's start with a diagram. The key to this problem is to draw this correctly. We can go ahead and label each mass 1 through 4. This will help us associate each mass to each other. We can also draw a right triangle with side lengths r, r, and r root 2. We can also determine from this that the angle from the horizontal from 1 to 2 is 45 degrees because this triangle symbolizes a 45, 45, 90 triangle with a right angle 90 at the center of the circle. Let's begin to look at the calculations necessary. We need to first identify what forces are acting on each mass. Since they are all identical, the forces acting on mass 1 is the same as the forces acting on the others. Now, since the masses are moving at a constant speed, we are only concerned with the perpendicular component of F net. We can write this expression as shown. F2 and F3 both have an angle affecting the strength of those forces, while F3 is just straight across the center of the circle. Now we can begin to solve this problem. We know the equation for gravitational force acting on different masses as g times m1 times m2 divided by the radius squared. We can plug this into the equation for each f. However, the distance r of f3 is different than the distance of f2 and f4. From the diagram we drew earlier, we know that the hypotenuse of that triangle we drew was r root 2. So for f2 and f4, that is our r. Then it's just a matter of plugging in the right values. The correct value for F net perpendicular is shown at the bottom, circled in red. Since we are looking at circular motion, we can relate the F net perpendicular we just calculated to the equation for centripetal acceleration. So we can set PV over R equal to the equation we just calculated on the previous slide. This process is shown here. Since it makes it simpler, we can leave the velocity for now in terms of velocity squared. That answer is shown circled in red on the right. Now, the goal of this problem is to calculate the time for one revolution. We can use the equation shown in the upper right. In the previous slide, we calculated velocity, and now we can just plug that in here. Since we kept velocity squared, we can write this expression as t squared. This isn't really necessary, but it makes the final answer a little bit neater. To get this final answer, all we need to do is take the square root of the whole thing. As you can see, you can pull 4 pi squared out to just be 2 pi. Again, this isn't necessary, but it makes your answer neater. And it's as simple as that. The final answer is shown at the bottom, circled in red. Thanks for watching.